The Cassegrain telescope is an advanced type of reflecting telescope, improving upon the original design invented by Isaac Newton. Unlike refracting telescopes, which use thick, heavy lenses that can distort colors, reflecting telescopes only require a thin layer of glass to create a mirror. This makes them more efficient, lightweight, and capable of producing clearer images of celestial objects. The Cassegrain design is particularly beneficial because it folds the long focal length into a compact structure, making it easier to use and transport. A Cassegrain telescope consists of a large primary mirror and a smaller secondary mirror, which work together to reflect and focus light toward an eyepiece or digital camera. In our simulation, we will set up the telescope with the following specifications. Primary mirror diameter, 25 centimeters. Primary focal ratio, 8, resulting in a focal length of 200 centimeters. Eyepiece focal length, 1 centimeter. A larger primary mirror collects more light, making celestial objects appear brighter and clearer, similar to how a larger pupil allows more light into the eye, improving visibility in the dark. The focal length determines how much the image is magnified, with a longer focal length resulting in a more detailed view of distant objects. When we start the simulation, we observe how light enters the telescope and is manipulated by its mirrors before reaching the eyepiece. The path of light is as follows. 1. Light from Jupiter enters the telescope and strikes the primary mirror, marked as A. 2. The primary mirror reflects the light toward the secondary mirror, which is positioned above it. 3. The secondary mirror redirects the light through a hole in the primary mirror, sending it toward an eyepiece or digital camera. 4. The light reflects off an additional flat mirror before reaching the eyepiece for final magnification. The image seen in the eyepiece represents what Jupiter might look like through the telescope. In real-life astronomy, observers often use digital cameras to capture images over time, enhancing the clarity and detail of celestial objects. However, even with the naked eye, one should be able to observe Jupiter's bands and atmospheric features through the telescope. At the top left of the simulation, we see how light reflects off the two curved mirrors before reaching the eyepiece. The law of reflection states that when light strikes a mirror, it bounces off at an equal angle on the opposite side of a normal line, a perpendicular line drawn at the point of reflection. Even though Cassegrain telescopes use curved mirrors, the reflection follows the same rule at every point on the surface. The simulation visually demonstrates how light behaves when striking the curved mirrors, guiding it efficiently toward the eyepiece. The Cassegrain design is unique because it allows a long focal length to be folded into a compact telescope body. This makes it possible to achieve high magnification without requiring an impractically long telescope tube. The magnification of a Cassegrain telescope depends on two key factors: the focal length of the primary mirror, how far it focuses light; the focal length of the eyepiece, how much the image is further refined. Since the primary focal length in this simulation is 200 centimeters and the eyepiece focal length is 1 centimeter, the resulting magnification is very high. This makes distant objects appear much larger, but it also reduces the field of view, meaning that less of the sky is visible at once. The simulation allows users to adjust various settings and see how they affect the final image. By experimenting with different parameters, we can explore various astronomical viewing conditions. Increasing the primary mirror diameter results in brighter images as more light is collected. Changing the focal ratio affects the balance between magnification and field of view. Adjusting the eyepiece focal length alters the size and clarity of the final image. By tweaking these settings, students and astronomy enthusiasts can observe how different telescope configurations affect visibility and image quality. If you have never seen Jupiter through a telescope, This is a fantastic opportunity to do so. With a properly configured Cassegrain telescope, you can observe the cloud bands of Jupiter, which are giant storms in its atmosphere. The 4 largest moons, Io, Europa, Ganymede, and Callisto. Jupiter's famous Great Red Spot, a massive storm larger than Earth. The simulation provides an approximation of what Jupiter might look like through the eyepiece. In reality, astronomers take multiple images over time and process them using computer software to reveal even more details. The Cassegrain telescope is widely used in astronomy due to its numerous advantages. 1. Compact and portable. Unlike long refracting telescopes, the Cassegrain design folds the optical path, making it shorter and more manageable. 2. Minimal optical distortions. Mirrors eliminate color distortion, chromatic aberration, that occurs in lens-based telescopes. 3. High magnification. The long focal length allows detailed observations of planets, stars, and deep space objects. 4. Ideal for imaging. The secondary mirror allows cameras to be easily attached, making it perfect for astrophotography. However, high-quality Cassegrain telescopes can be expensive, as precision engineering is required to manufacture the curved mirrors accurately. The Cassegrain telescope is an incredible advancement in telescope design, building upon the reflecting telescope invented by Isaac Newton. By utilizing curved mirrors, it eliminates the need for heavy lenses and creates a compact yet powerful optical instrument. Through this simulation, we observe how light enters the telescope, bounces off the primary and secondary mirrors, and is directed toward the eyepiece or camera. By experimenting with different configurations, we can explore how diameter, focal length, and magnification affect image quality.